Separation of variables is really a very powerful method to solve PDEs, and is really an emphasis for this course. So now I do the first example for separation of variables to show you what's to come. Don't worry if you don't get this 100% for the first try. We will do this so often that we all get sick of it. Okay, let's dive right in. The key idea is to use a separation of the variables, as the name says. So where we have a solution u of x and y, we want to write this as a product of two functions, one only depending on x and the other one only depending on y. So f of x times y of y. We have seen these kind of solutions before in one of the examples, where we had a function un depending on two variables as cosine of nx and hyperbolic sine of ny. Okay, and this is basically what I have in mind. So I want to find functions, one depends only on x, the other only on y, and I have no idea if this works. Which is not quite true, because I do know it works, because I've done it. But at the moment, it is just an idea which might be useful to solve PDEs. So let's look at this example. We have a heat equation. du by dt is k d square u by dx square with homogeneous Dirichlet boundary conditions. So at 0, the temperature, say, is set to be 0. At L, the temperature is 0. And we have an initial condition. F of x is 3 sine of 2 pi x divided by L. Let's apply the rule of thumb for the side conditions. So we have one time derivative, which means we need one initial condition. And we have two spatial derivatives, so we need two side conditions or two boundary conditions, which we have. So the number of side conditions is perfect. We will be able to solve this problem. So let's come to the idea, u to be x times t. Now, since one variable is called x and the other variable is called t, I denote the function accordingly. So x is a function of little x, big T is a function of little t, just to keep the notation intuitive. Okay, so now we differentiate this product by time, du by dt, and then of course only the t function depends on t. So then this is x of x times t prime of t. If we differentiate this by x partially, then only the x function depends on x and the t function does not. So for the first derivative, for example, we can write d by dx of u would be then d by dx of big X times t. So this only involves the x. So then we have this is x prime times t. Good. And then doing it twice, we get x double prime times t. So we can substitute these expressions now into the heat equation. Let me just rewrite the heat equation. ut is k times u xx. Okay, for ut we have x times t prime, and from k u xx we have k x double prime times t, just from above. Okay. So now we can divide this equation by kt and by x, and then we get t prime divided by kt equals x double prime divided by x. But now a little miracle happens, because the left-hand side only depends on t, on the independent variable t, while the right-hand side depends only on x. But they have to be equal. There are two functions depending on different things, but they have to be equal. So the only choice they have is to be constant. The left-hand side must be constant, the right-hand side must be constant, but there must be even the same constant. And so this constant we call minus lambda. Now there's a discussion sometimes if you should call it lambda or minus lambda. Now we agree to call it minus lambda, but it's so far it's just any odd constant. You can put a minus sign or not, it doesn't matter. It turns out though, if you put a minus sign, it looks a little bit nicer in the end. So we call this minus lambda. So then t prime over kt is minus lambda, and x double prime over x is minus lambda. So then the left equation only depends on t, and the right equation only on x. And this is actually really cool. So taking each of these, we rewrite them once again. So then we multiply this one by kt, and we get t prime plus lambda kt is 0. And for the x equation, we get x double prime plus lambda x is 0, where we multiply it by x. But these are ODEs. These are ordinary differential equations, and we might have a good chance to solve them. So we get separated ODEs for t and x. Now let's look at the boundary conditions. So u at 0 has to be 0, but now written as a product, this is also x at 0 times t of t. And similar at the right, u at L is x of L times t of t is also 0. Now, making the product 0, we have two choices, right? We can say x at 0 is 0, or we can say t is 0, identically as a function. But the 0 function is not a good choice, because then we only get the 0 solution, which would not satisfy the initial condition. So t of t equals 0 for all t is not an option, and we need to have x at 0 is 0, and x at L is equal to 0. So these are then two boundary conditions for the x equation. So let's add them to the problem. So then we get a time problem, t prime plus lambda kt is equal to 0. And we get a spatial problem, x double prime plus lambda x is 0, with boundary conditions x at 0 as x at L is equal to 0. Let us solve the time problem first. So the time is just an exponential equation, right? We can write it t prime is minus k lambda t. So then it's solved by the exponential. A constant times e to the minus lambda k times t. Okay, so you should remember from your course on differential equations that x dot equals alpha x is solved by a constant e to the alpha t. We will actually make use of ODE theory quite a bit more now. Okay, so we have solved t. Next we need to go to solve for the x equation. Now it turns out that the x equation can only be solved for certain values of lambda. Not for all lambda, just for certain values. And these values we call the eigenvalues. And then the corresponding non-trivial solutions are called the eigenfunctions. So what we are now up to is we are hunting for the eigenvalues and hunting for the eigenfunctions. So here's the x problem again. We can only solve it for certain values of lambdas, which we like to find now. We need to look at three cases. We need to look at the case lambda negative, lambda positive, or lambda equal to 0. So case 1, if lambda is negative, we write it as a minus mu square, where mu square is a positive thing, so the minus sign makes it negative. And then the x problem becomes x double prime minus mu square x is equal to 0. So again, we have to employ ODE theory. If you want, you can write this as x double prime is mu square x. And this is solved by the hyperbolic sine and cosine functions. So the general solution for this ODE is A cosh mu x plus B sinh mu x. Right here. To find the A's and B's, we use these side conditions again. So one condition was x at 0 is equal to 0. So we can sub it in there. Cosh at 0 is equal to 1, sinh at 0 is equal to 0. So we could write this to be equal to a times 1 plus b times 0. So then we get a is equal to 0 from this relation. For the side condition for b, We now are left with the function x-axis b sinh of mu x. We sub in xl is 0, so this makes it b sinh of mu l is equal to 0. Now this can only two possibilities, either b is 0 or the hyperbolic sine of mu l is 0. So let's look at both possibilities. If the sinh mu l is 0, this means mu must be equal to 0. But if mu is equal to 0, this is actually excluded, because then lambda would be 0, but we said lambda should be less than 0. So here the only option is b is equal to 0, but then the function x would be 0, and again we find the 0 solution, which does not satisfy the initial condition. So that's no good, no good, no good, no good. So here for the case 1, we find no useful solution to our problem. For the next case, if lambda is equal to 0, then the equation becomes x double prime is just 0. So we can integrate this again. We get x prime is equal to a constant a. And then x itself is ax plus b. Now we use the boundary conditions again. So x at 0 should be 0. So this makes it to be a times 0 plus b, or simply b, and so then b must be 0. And if we sub in the l, then we get 0 equals al, so then a must be 0 also, and again we get the 0 solution. So no non-trivial solutions. Now let's hope that for lambda positive we get something useful. So we write lambda to be mu square, then we get the equation x double prime plus mu square x is 0, which we can write as x double prime is minus mu square x, if you like. And the solution, based on ODE theory, would be given by sine and cosine. So the solution is a sine mu x plus b, a cosine mu x plus b sine mu x. And again we play the game with the boundary conditions. So we sub in x is 0, cosine at 0 is 1, sine at 0 is 0. So we get a times 1 plus b times 0. So then we have a is 0 from this one. On the other boundary condition, then at L, we sub in L, a is already 0, so we only just keep b times sine mu L is equal to 0. Again, we can have b is 0, which is no good, or we can have sine mu L is 0, which is maybe better. Who knows? Oh yeah, the sine function actually is 0 many times over, right? Here just plotting the sine. It's always 0 at multiples of n times pi. So this means when the argument mu L is equal to n pi, then we get zeros, and we can satisfy this equation. And this happens for n is plus minus 1, plus minus 2, and so on, and so on. So we get non-trivial solutions for particular values of mu, which are given as n pi divided by L. And this means particular values for lambda, which is just the square of this. So n square pi square over L square. Hey, that's very neat. So we do find something useful. The eigenfunction here, x would be b sine of mu x, where now for mu, we use the mu n's, which we just computed. So then we get those to be sine of n pi x divided by L. So then we can put this together with the t function from earlier. Okay, t was the exponential, but now we have specific forms for the lambdas. So we get e to the minus lambda n kt, where the lambda n are from before, n square pi square over L square. And then we get solutions of the form xn times tn, which we can write out to be bn e to the minus lambda n kt sine of n pi x divided by L for n is 1, 2, 3, and so on. There's one side condition we haven't used, which is the initial condition. So u at x0 is f, and f was given by 3 sine of 2 pi x divided by L. Now if you compare this to the general solution upstairs, we see there's a very good match, right? instead of n pi x over L, we have 2 pi x over L. So this is a term where n is equal to 2. Ha! This works here wonderfully. So this means the Bn, the coefficient, must be the 3 in front. So to make it match really perfectly, the exponential term is 0 because we are choosing t is equal to 0 in that condition. All right. So then we have the Bn, which is 3. The n is equal to 2. And then this will be our solution. 3e to the minus 4 pi square kt divided by L square sine of 2 pi x divided by L. And I subbed in the lambda 2 into the exponent. Okay. So this works out really nice. This is our example for separation. Now there's a little bit more to it. If you look at this general form for the un, we still have the superposition principle, which means in general we can allow linear combinations of these. And this is what I'm showing here. We can allow a sum n is 1 to infinity bn un. So we can sum up all these kind of terms and make many, many more solutions to many more, much more complicated initial conditions. This is called a series solution, and we will study series solutions in more generality as we move along through the course. All right, so yeah. This was quite some work, so done with this one. See you next time.